Hello and welcome to the first video covering chapter 8. Okay, so there's going to be two videos for this chapter. In this first video covering the first half of the slides for chapter 8, I'm going to talk about the sun, kind of what are the specifics of our local star, the sun. How do we talk about the key terms for its layers, its atmosphere, what goes on inside. Okay, so one part of this first lecture is going to be the actual physics of how the sun generates energy. Okay, so we'll talk about that briefly, right? Basic idea of it. And then we'll kind of culminate this lecture, this first video, by talking about the cycle of the sun. It has a certain, a 13-year cycle. We're going to see how that behavior is mapped on its surface and what that means, and how scientists make measurements about the sun. Okay, so you can see it's kind of key terms, some physics, and then some overall kind of trends in the science and all involving our sun, right? So specific on it. There's a lot we can talk about. We're just going to get into the few of the details because we're still talking about our solar system, okay? And we know a lot about our own solar system because, consider that's what, besides the last lecture when we talked about exoplanets, we've been talking about how we understand the gas giants in our solar system, how we understand the terrestrial planets in our solar system. Close to home, lots of detail. Same thing with the sun. But here's the great thing. In the second half of this chapter, so the second set of lecture slides will be in the next video, then I'm going to get into how we compare our sun to other stars. Because our sun is part of a continuum that makes us able to understand stars across the entire galaxy and beyond the galaxy, okay, in other galaxies. And that is remarkable, thinking about how the sun is part of a bigger picture and the wide and wonderful world of categorizing stars. Okay, so that's going to be all about the second half of the chapter. All right, so let's finish up talking about the solar system and then start our mini chapter journey into looking outside the solar system at other stars. Okay, all right, so first, our sun. Okay, so properties of the sun. Okay, we want to talk about how we measure something called stellar luminosity. Okay, how do we talk about stellar temperatures? And how do we talk about masses? Okay, so we can see these are very much like key physical characteristics. Mass, measured in kilograms, temperature, measured in Kelvin, and luminosity, measured in watts. Okay, which is power. All right, so why does the sun shine? What is the sun's structure? Okay, so here is the sun as viewed through the X-ray part of the electromagnetic spectrum. Okay, so these are all the X-rays coming off of the sun. The brighter spots would be higher concentrations of those X-rays. Okay, the dimmer areas, lower concentration. Pretty remarkable. Okay, X-rays are high energy light. Okay, so is it on fire? Well, that's a good question. Okay, certainly people thought so for hundreds of years. But if we were to think about the chemical content, because fire is a chemical process, well, divided by the luminosity, which is just the power output of the sun, it could only burn for about 10,000 years. It would use up all its fuel if it was burning like a traditional fire. Okay, if it was like a molecular fire, which is, like wood burns or, a gasoline fire or something, right? Fossil fuel fire, 10,000 years. And that's it. And the sun's huge, but, combustibles burn fast. Okay, so we talked about how the gas giants generate heat through contraction, okay, or even differentiation. They're still sinking and separating the heavy material down. That releases energy, and things fall, they release energy. Well, that's a good question. Is it contracting? Okay, well, if you think about its size and its luminosity, how much potential energy it has, perhaps it's getting denser inside. Okay, consider its luminosity. You get a lot more time because you can have a very gradual contraction, which releases a huge amount of energy if it is collapsing in the interior. But even then, it can only be about 25 million years old. Okay? So, think about this number. By the way, this 10,000 number, this actually coincided with a movement in science to accept a somewhat, let me be honest, very non-scientific idea that the world was only 5,000 years old. Okay? And that things like fossils were misunderstood and plate tectonics couldn't be possible. This was only like about 120 years ago, by the way. It was fairly recent, where that did get some mainstream ideas. And scientists looked to this idea that the sun could only be 10,000 years old, because they couldn't imagine that there was another source of energy. It's obviously burning. You look at it, it's a big bright ball in the sky, right? But of course it's not. We now know it's not. Okay, so that's, that 10,000 years, that ties in with that. Have you ever heard about the 5,000-year-old Earth? Right, this is the 10,000-year-old sun, but it's wrong, okay? It's the wrong idea. And it's also not gravitationally contracting. Just 25 million years, although it was a lot of time, it's not a lot of geological time, right? There are, the dinosaurs are around 65 million years ago. Furthermore, the sun is much older than that. The rocks that we carbon date in primitive asteroids, right? How old are they? 4.5 billion years old, okay? So it's definitely not contracting. So this is it. It's nuclear energy, okay? All right, just like in nuclear power plants, but also not quite like in nuclear power plants. It's the other kind of nuclear energy, all right? And that puts its age at about 10 billion years, give or take a billion years. Okay, we're not exactly sure, but the models put the fact that the sun will eventually die after 10 billion years. More on that later. We get to talk about the life cycle of stars, pretty cool stuff. And if you might recognize the formula, E equals mc squared. Okay, we'll come back to that. That's Einstein's formula of special relativity, part of it, okay? All right, so let's think about it. What's going on in our sun? Well, the weight of the upper layers compress the lower layers, kind of like in our atmosphere, okay? Or kind of like in a gas giant. Think about the cores of the gas giants, Jupiter, Saturn, right? They have those metallic hydrogen cores because they're under such high pressure, okay? So that's a common phenomenon. Dense cores to these giant solar masses. The sun is huge. That's a lot of weight. Okay? So what happens, however, is something called an equilibrium is established. It's a balancing. It's a balancing between all that weight crushing down on the interior of the sun and the interior of the sun pushing back. But how does it push back? We kind of take that for granted. We think of a solid, we think of the Earth, right? Well, why doesn't the Earth just collapse in on itself? It's like, well, a rock is solid. It holds it up. I mean, we have a molten rock core, essentially, so that's incredibly dense and it pushes back. And that's true, okay? The fact that the Earth is pushing on the core keeps it molten, keeps it melted, because that's still a lot of heat, and there's leftover heat. We talked about that. But from the Earth's formation, that is. But there's a bigger question here, and that's the idea. Well, if the Earth was bigger and the push was even more, then you could collapse that denser material. You could push it down until it couldn't push back anymore. And it turns out when that happens, you affect the actual inside of the matter itself. You affect the nucleus of the matter, and you get nuclear processes just from that crushing pressure of gravity. You press on the matter so much, you fundamentally change it. And when this matter is a gas and isn't heavy elements like we have on Earth, that pushing process happens readily, I guess, to think about it, right? And it can create a fundamental change inside of the atoms. And when that happens, energy is released. Think the nuclear bombs, think nuclear energy plants. So nuclear means energy, and huge amounts of energy, right, for relatively small amounts of matter. And that pushback, it holds gravity at bay. And that's it. That's the only thing that holds gravity at bay, because otherwise gravity would win. Okay? But the nuclear energy pushes back. And think about the idea that scientists had to speculate on the existence of nuclear energy being the source of gravitational equilibrium, which just means balance, inside the sun, and the source of the energy to explain the age of the sun, before we had proven that nuclear energy even existed, before we actually had done things like split the atom, okay, or fuse hydrogen. All right, that's kind of fascinating, isn't it? Okay, but that energy supplied by fusion of the atoms maintains the pressure that balances the inward crush of gravity. All right, this is an energy balance. The rate at which the energy radiates from the surface of the sun must always be the same as the rate at which it is released by fusion in the core. Okay, so the core is pushing it back against gravity. It's releasing energy. Okay, that outward pressure that's associated with the release of energy keeps the size of the sun and its density fixed. But there's also energy. The energy is in the form of wiggling atoms. The energy is in the form of light. And that energy, all we're saying here is it has to make it to the surface. It can't get trapped inside, because otherwise that would mean the sun would be constantly growing hotter or growing bigger or both. Okay? But the energy is being radiated away. So that it's an energy balance as well as a weight equilibrium, as a force equilibrium, right? So it's a force equilibrium, gravitational equilibrium, force equilibrium, whatever you want to call it. It's also an energy balance. Just as much energy is being produced by fusion as is coming off of the surface. Okay, and all the energy that comes off of the surface of the sun, it all radiates in the form of light. Lots of different spectrums of light, including the visible spectrum, primarily the visible spectrum as well. Okay, and that's it, right? Because it can't produce any other form of heat, because heat doesn't flow through space except for light. Okay, so the gravitational contraction was how the sun was formed. We'll talk more about the life cycle of young stars in a later chapter. But that's how it heated up the core in the first place, during formation. But once that gravitational equilibrium was achieved, 2 slides back I mentioned it, that's when the contraction stopped. And then ever since, the sun has remained constant in size. Okay? Okay, but it shrunk down to its size, and it, kind of when it fired up, when the engine first started. That happened because it's crushing in on itself for a while in this formation, right? Can you imagine that? Like the gas cloud collapsing, eventually forming what's called a protostar, and then that protostar kind of starting up. The first fusion firing, and more fusion leading to more fusion, chain reactions, huge amount of heat. Star stops contracting. Now it's a stable star. Okay? And then it's still got some growing pains, probably a lot of leftover gas, and right, but then eventually planets are starting to form at this stage, right? You can just imagine a primordial solar system. Okay? So let's cover the structure. These are just all key terms here. Okay, we're just going to go through them. All right. So first of all, some important numbers. The radius of the sun is 6.9 times 10 to the 8 meters. That's 109 times bigger than Earth. You can think of the sun as being 110, Earths across. Okay, but if you have 110 Earths across, then you sure have a lot of Earths to fill a volume, right? You think about 110 Earths across as like stacking them up like this. Well, that's a lot of total Earths in a 3-dimensional space. So it turns out the mass of the sun is 2 times 10 to the 30, so that's 30 zeros, kilograms, right? Yeah, it's big. Okay, that's about 300,000 Earths. So 300,000 Earths would fit inside of the sun, okay? All right, luminosity, this is its wattage, right? So you think of a light bulb, maybe, an LED light bulb has like 10 watts, right? This one has 3.8 times 10 to the 26. Okay, that's a really huge number, right? Okay, so first we'll start on the outside in. Let's just cover all the aspects of the sun. Okay, well, all of them, no, right? But we're covering the basics. Okay, solar wind, go back, solar wind. All right, this is a flow of charged particles from the surface of the sun. I've mentioned this before, we talked about it with comets. It's primarily electrons. So you think of the solar wind as primarily being formed of electrons. That's it, so it's a bunch of shedding electrons. It's like electricity coming off of the sun. There's a lot of it, it's a solar wind. Our magnetic field primarily diverts it from Earth, okay? All right, so that's kind of the thing that immediately permeates away from the sun. And it's real strong when you're close to the sun. It gets weaker the further away you are, okay? Then we get to the corona, okay? This is the atmosphere of the sun. It is incredibly hot, okay? Now here's the thing, okay? Here is the thing. First of all, the corona, it's beautiful. It's what people see when they look at a total solar eclipse, all those pictures of the total solar eclipse. It's that kind of wavy smear around the black hole that, the black spot that is the moon covering the sun, okay? If you don't know what I'm talking about, look at a picture of a total solar eclipse. You'll recognize a corona right away. It's normally not visible because it's not nearly as bright as the surface of the sun, so it gets washed out by the surface of the sun. Make sense? Okay? But why is it so hot? Okay? I mean, that's crazy. When you'll see that once we just go down to the surface of the sun, the part we can see called the chromosphere, it's going to be like, orders of magnitude cooler. So what could possibly make the atmosphere hotter than the surface? Well, okay, if you remember, this is an idea that we already saw. Our own atmosphere is hotter than the surface. And just remember, temperature does not mean heat. Temperature is just the average kinetic energy of the atoms or molecules in a gas, okay? As well as in a solid, but here it's a gas, it's an atmosphere. And so if you don't have many of them, if you have a very low density atmosphere, then that means that they're going really fast, but there's so few of them, there's not that much heat. So yeah, the atmosphere is hot because it's a few particles bouncing around very quickly, but it doesn't actually contain that much temperature. Okay, our own atmosphere is really, really hot. But if you were there, you would freeze because very few molecules would actually bump into your skin to pass the energy on to you. Okay, Same with the sun's atmosphere. It's incredibly hot. You wouldn't have to worry about freezing in it, unlike our atmosphere, because it's so hot that you would still actually feel hot. But it wouldn't be like 1 million Kelvin if we had a 1 million Kelvin, say, liquid, okay? Or 1 million Kelvin, basically plasma in a liquid state. Now that would be hot, okay? That would be unbelievably hot. The corona is very low density. Okay, so that's my rant. Temperature does not mean heat, okay? By the way, it actually still is interesting that it's that hot, but again, we see that in the atmosphere around the planet, right? Our upper atmosphere is way, way hotter than the surface. All right, so now let's get to the temperature of the surface. This is a number we care about a lot, okay? All right, oh, I forgot the chromosphere. No, I didn't. I did, yeah. So the chromosphere, I misspoke. The chromosphere is still the atmosphere. It's the part that's kind of the glowing halo around the sun. It doesn't show up that much in the in eclipses. I guess it's part of it. It's certainly part of it when you have a ring of fire eclipse. We mentioned this briefly in a previous chapter. Also called an annular eclipse. But the important thing is still the atmosphere. It's still hot, so like 10,000 to 100,000 Kelvin. So it's kind of just gradually falling. It's almost like a linear decrease from the million Kelvin in the upper atmosphere of the corona, which is very far away. But you're going down. Okay, so again, chromosphere, kind of a middle layer, doesn't get talked about too much. Let's get to the important part, the photosphere. Okay, now this is the photosphere. This is the actual surface of the sun. When the ball of gas gets so dense that this is the part that looks like a solid. It isn't transparent. Okay, the corona and chromosphere were transparent, especially considering how bright the photosphere is, the surface. Okay, and this is the temperature. This is the temperature that we care about the most. This is the 6,000 Kelvin, because this sets the color of the sun. And we'll talk about that in this chapter, second lecture, second video. Okay, so 6,000 Kelvin, right? We've sure gone down a lot from a million. Okay, still really hot. Okay, but that's the surface of the sun. It's 6,000 Kelvin. Okay, and by the way, you'd feel much hotter here at 6,000 Kelvin than you would in the chromosphere at a million Kelvin. Now, you would probably have to be an incredibly sophisticated spacecraft to some time, because both those temperatures would actually, even at the low density of the chromosphere, wouldn't work for a human. You'd die. You'd die from the X-rays too, okay? Even in a spacesuit. But, yeah, definitely, right? But here, because this is the surface, this is dense, this 6,000 would feel way hotter than the million in the atmosphere, okay? Okay, this is when the sun melts anything that touches it, okay? 6,000 Kelvin. Now, we dive into the surface of the sun. Obviously can't do that. You can't send a probe into the surface of the sun. It would absolutely not be able to withstand those temperatures, okay? And the incredible gravitational crushing force of the sun, right? There's a lot of gravity, okay? All right, but this part that we speculate on based on models of the sun and behavior on the surface and something called neutrinos, okay? Well, it's like the convection layer of our planet. It's got big convection cells that are going around. That's moving gas. It's like the mantle of Earth, but also very, very different substance, because it's all formed out of plasma, super hot plasma, ionized gas, that is. Okay? So that's the convection sun. It's convecting heat as the bulk movement of fluids. In this case, though, the fluid is a plasma, an ionized gas. Okay? Then we get down to what's kind of the radiation zone is a good name for it. It's essentially the highly dense, very high pressure part of the sun, but where there's no fusion occurring. Okay? It is incredibly dense. Radiation here moves very slowly. We'll talk about how slowly photons actually move through the radiation zone, because they have to bounce around through it. They think of the photons as being little particles, like a ping pong ball, bouncing around through some sort of like crazy grid system that it has to, bounce through for, tens of thousands of kilometers, millions, millions of meters, millions and millions of meters. Okay, so that's it. Okay, radiation zone, or kind of I think of the inert shell of the core is another way to think of it. Okay, but here's the term, radiation zone. Okay, now we get to the core. That's it. There's no sublayers of the core. Okay, not for this discussion. There's just the core. The core is 15 million Kelvin. Okay, so it's the only part of the sun that is appreciably hotter than the corona. Okay, but it's 15 times hotter, and it's hot enough. It's hot enough and it's dense enough that it allows for fusion to occur, which we'll discuss. Okay, so 15 million Kelvin. This is incredible high temperatures. These are temperatures and pressures so great that the very properties of matter are changed because of this, because of the incredible environment that this is. Okay? All right. I mean, this is like, really high energy physics ideas. All right? So that's the core of the sun. All right? So in summary, chemical and gravitational energy sources could not explain how the sun could sustain its luminosity. And the sun shines because gravitational equilibrium keeps its core hot and dense enough to release energy through nuclear fusion. We learned about the layers of the sun. Okay? Okay, now the fusion. What goes on inside the core? How does nuclear fusion occur in the sun? Okay, because it's hot enough for it to start, but what was it that started exactly? How does this energy from fusion get out of the sun? Okay, and how do we know what is happening inside the sun? All good questions, right? Okay, what the heck is fusion? Okay, well, fusion is fusing things together. So it's bringing things together. And it's bringing together atomic nuclei. Specifically, it's bringing together two hydrogen. And the hydrogen are each just a single proton. Okay, so this would be hydrogen plus. Hydrogen plus. Why plus? Because it's been ionized and it's lost its electron, so it's not neutral hydrogen. It's just hydrogen with one proton without an electron. Okay, so you think of either as H plus or P. P for proton, hydrogen plus for ionized hydrogen, or H plus for ionized hydrogen. They smash together and they fuse together. Okay, they fuse together into a new nucleus. Okay, so there's two types of nuclear processes. There's fission. This is what happens inside all nuclear power plants and most nuclear bombs. Okay, there are also fusion bombs, but most bombs, including the only ones that have been dropped on people, are fission nuclear bombs. Okay, and nuclear power plants all generate energy through fission. Fission is taking a big nucleus like uranium and splitting it apart, and that releases energy. Okay, all right. Fusion, on the other hand, is what happens inside of the sun. On Earth, it's never been used for commercial production of power, like a power plant, a fusion power plant. Okay, there are a lot of, or at least a couple prominent prototypes of commercial fusion power plants being attempted to be built. Fusion occurs in the laboratory, and as I said, there's also some of the most powerful nuclear bombs that have ever been tested are fusion nuclear power bombs. So fusing together small nuclei like hydrogen or helium, but especially hydrogen, to make a bigger one. And this also releases energy. So there's a funny thing about elements and about the fundamental forces of nuclear energy that make it so when you split apart big atoms, big nuclei, you get energy. And when you smash together small nuclei, you also get energy. So each of these create energy. Okay? But if you were to split apart a small, like if you were to go backwards here, if you were to split apart a small nucleus, one here that only has two particles in it, two nucleons, okay? Well, you're actually going to not get any energy. You're going to lose energy if you were to force them to split, if you were to force this to split apart. Likewise, if you were to force the fusion between these two, which are the byproducts of, say, uranium fission, maybe they're like plutonium and neptunium or something, if you were to fuse them together, you could, but it would take a huge amount of energy. It wouldn't generate energy, okay? So it's interesting. There's these energetically favorable paths for big things and small things, and they're opposite, okay? Okay, so why is it that fusion requires the core of the sun to work, okay? Because the reason we don't have it more commonly used, say for commercial power plants here on Earth, is it's hard to do. You need very, very high temperature to enable nuclear fusion to happen. You don't need that for nuclear fission. You can use other tricks, okay? But for fusion, you need very, very high energy because at lower speeds, when the energy isn't crazy high, what happens is the two protons, those ionized hydrogen nuclei, they don't actually smash together because they get repelled by electromagnetic repulsion. There's a property that says in physics that like particles repel, opposite particles attract as far as charge is concerned. Protons are the same charge type, they're both positive, so they repel each other. Okay? But if they're going fast enough, because it's hot enough, and remember temperature after all is just related to average kinetic energy of a substance, then you know what happens? They actually do come close together. They overcome that repulsion. And here's a weird thing about physics. then they actually get held together by another force, a weird, mysterious force called the strong nuclear force that only operates at really tiny operating distances and is much stronger than the electromagnetic repulsion force. Yeah, that's a weird one. But we do have some good understanding where it comes from. Scientists have done experiments to determine the particles that actually transmit this strange force. Why it has such a short range, I can't tell you, but maybe it's inherent in the type of particles that propagate it. Okay, so what's the type of fusion that there is? Well, there is 4 protons, right? There's our 4 ionized hydrogen, okay? And this one here isn't showing the charge of the hydrogen. Instead, it's showing the fact that this is H1, that it only has an atomic mass of 1. That's in contrast to other isotopes of hydrogen, the only common one of which is called deuterium, which would have a 2 here instead of a 1, because it would have 2 nucleons, one of which would be a neutron. But that's really rare. That's what makes heavy water, if you've ever heard of heavy water. But vast majority of hydrogen just has 1 single particle in its nucleus, okay? Anyway, but it's also ionized. And so those are our 4 protons, hydrogen nuclei. They come together, and look what happens. They form, due to fusion, due to overcoming that electromagnetic repulsion force, they form a new thing. They form a stable nucleus that isn't just going to fall apart. It's going to stay together now. And it has 2 protons and 2 neutrons, okay? And it is helium-4. And it is actually neutral helium-4 because it has just as many neutrons as protons, okay? I guess it's still ionized, but I should say it's the standard non-isotopic version of helium because it has just as many neutrons as protons, which you expect for small elements. Now, but all that aside, look what happened. 2 of the protons, at least, 2 of them, they became neutrons, okay? So that's the whole process that's happening. That's something that can happen with high energy, and that's part of the whole fusion process. And probably more importantly than the protons changing the neutrons, just the fact that there's 4 of them bound together and what that means on a fundamental quantum mechanical matter wave physics sort of sense is that the actual total energy of that structure has changed and it's reduced. And so there's a lot of energy produced, okay? There's energy released from the fusion. Interestingly, most of that energy, and I didn't know this for years as a physics student, so I'm telling you, most of that energy is actually the kinetic energy of the product of the fusion, the actual helium, okay, as well as protons that were used up that didn't, that kind of got ejected from the chain of fusion, which we'll talk about in just a minute. So most of it's kinetic energy. But you think, well, the sun's all about, changing matter to pure energy. It is. It's changing it to kinetic energy because matter did disappear. These 4 protons here weighed more, okay? On a fundamental level, they weighed more than what they became when they fused together. Mass was lost, and that mass became energy, okay? Now, again, it mostly becomes the kinetic energy, which is important because after all, it's got to push back against gravity. But a lot of it does, not a lot of it, but a good portion of it, not the majority of it, also becomes actual pure light photons. And those photons are what's going to come off of the sun. There's going to be more various levels of vibration and the production of more photons from different energy processes because any vibrating thing anytime it's accelerating and it's a charged particle, it produces light, okay? It's one of the big properties, one of the big laws of physics, okay? So there's a lot of light being produced, but primarily initially from the fusion, it's the kinetic energy of the particles. Okay, so here's the actual chain. I've been talking about a lot of things, so I won't get into it too much, but we can see that there's 2 protons every time. So there's like a step 1, 2 protons come together, they form basically a isotope of hydrogen, so a proton and a neutron. Step 2 is then we bring in another proton, and now we form basically an isotope of helium because there's 2 protons, which makes it helium, but there's only 1 neutron. And then finally, 2 of these sets of 3 come together, 2 protons get rejected with a ton of speed, all right, which is great for continuing the process, right? Think chain reaction, right? These ones that are going to go along and then make for more fusion down the line. But then we finally have the byproduct, okay? The end result. And it's really the end result because this is just left over. So this is not going to get you, this is like ash, right? This is leftover matter that's going to stick around and then never Nothing's going to happen with it until it turns out when the sun is in its later years, when it's dying, it actually will start to do something with all that leftover helium. But for billions of years it won't, including right now with the sun operating as it does, it will not, okay? So, all right, let's continue here. This is just a summary of it, the overall reaction, all right? And this is called the proton-proton chain. And this is in comparison to other types of fusion that we know can occur, okay? And there's also some other products. There's gamma rays, that's the pure light. And then there's these two other things, positrons and neutrinos, okay? All right. So a positron is just a positively charged electron. It gets annihilated when it finds an electron, which then just produces more light. So not too much to worry about there. But the neutrino we're going to come back to. Okay? This is a good summary, all right? And here's a great number. This is the amount of mass that was lost every time. That's mass that's gone. Mass can disappear. And when mass disappears, it becomes energy, okay? And it's also not a lot per reaction, okay? So you can see that but you actually don't need a lot. Again, think of a nuclear bomb. That's a huge amount of energy. That's energy that equals to tons and tons of TNT, but the nuclear bomb weighs very little, okay? Okay, so what would happen inside the sun if a slight rise in core temperature led to a rapid rise in fusion energy? Think about this one. What would happen? Okay? Well, the core would expand and cool, okay? That's the thermostat, okay? I have this on the next slide. Yep. So the thermostat essentially regulates the sun the same way that your home thermostat has this feedback loop, right? So it has a temperature gauge. If the house gets hot, then it's going to turn on and start cooling off the house. When the house reaches the desired temperature, the thermostat's going to read that, shut off the cooling, okay? And then turn it back on when the house starts warming up again. That's a thermostat. It's a detective device, okay? The sun has natural thermostats, okay? I won't go over the details for real this time, but I will summarize that the decline in core temperature causes the fusion rate to drop, so the core contracts and heats up, okay? On the other hand, a rise in core temperature causes the fusion rate to rise, so the core expands and cools down, okay? Because random changes in temperature will inevitably happen in something as big and complex as the sun, but the sun regulates itself. See it? Okay? And by the way, when it cools down, that means that the fusion rate would decrease, which gets you back to where you started. And if it heats up, that means that the fusion rate would increase, which then would, bring the star back up to operating, energy levels. Okay? So remember that the radiation layer of the interior of the sun, and remember the idea that pure light is produced, gamma rays are produced from fusion, all right? And then again from the annihilation of the positron with stray electrons. Well, that energy that's produced inside the core gradually leaks out of the radiation zone in the form of randomly bouncing photons. And that process, I thought I had it here, but I don't. That process takes about 1 million years. So the actual light that we would see, like the visible spectrum light, takes a long time to get out of the core. 1 million years, okay? So it's kind of interesting. That means that we wouldn't know if there's a change in the core until 1 million years after it happened, okay? If we were stuck only looking at photons, but we're not. Because remember I said we're going to come back to neutrinos, okay? But hold that thought. Here's just the convection layer. It's just, this is one of the layers of the sun. This is talking about how all that energy from the core, where does it go? Well, it's going to heat up. So we have rising hot gas that brings the energy to the surface, right? Then the surface, we basically have bubbling hot gas. Okay, it's so dense it's behaving like a liquid, okay, but it's a plasma, all right? And that's going to shine. It's going to shine so hot, it's just generating a ton of photons that are flying out into space, okay? Also generating the solar wind, electrons, okay, accelerating them away. How do we know, though? How do we even know about the radiation level? How do we know about the core? How do we know about the convection zone? We look at the surface. We can look at the velocity of the surface to see how it's bubbling. This is using the same detection device that we talked about when we talked about exoplanets. This is the Doppler effect. Okay, is the sun moving away or towards us? We're going to see. Okay, and it's overall lighter on this side and darker on this side due to the rotation, and thus the Doppler effect is shown in this scale of dark to light, with negative being moving away from us and positive being moving towards us. Okay, so we have models for the sun. We have those vibrations like we just saw, and then we have that word again, neutrinos. Okay. So, in summary, patterns of vibration on the surface tell us about what the sun is like inside. Okay, here the Doppler shift tells us what's what's bubbling. Okay, this is a cool one that shows this is a model. Okay, we had the model shown in the dotted line, and then look how well it matches up with data we have, and including what's going on in terms of the temperature and the density of the layers as we go inside, all the way down to the core. Okay, all right. See, I went backwards. Core's over here. Okay, sorry, this is going right down to 0. This would be like, because look at the horizontal axis is fraction of the sun's radius. This would be all the way at the center. Okay, we get an idea of the density and the temperature. Right, see about 10 million. Okay, all right. But then there's neutrinos. They're created during the fusion, and they fly directly through the sun. So it turns out neutrinos are weird. They practically don't interact with matter. They just fly out of the sun, uninhibited, unburdened by all the protons bouncing around, all the neutrons bouncing around, all electrons. They just pass right through them. They're a very unusual particle. All right. So the observations of these solar neutrinos can tell us what's happening in the core, because they reach Earth at basically the speed of light. They're slightly slower than the speed of light, but basically at the speed of light. Okay. So early searches for solar neutrinos failed to find them. Okay, and it failed to find the predicted number of them. More recent observations find the right number of neutrinos, but some have changed form. Okay, I won't get into that. It's a fascinating thing about relativity and all this sort of stuff. But it did receive a Nobel Prize when they found out that neutrinos were changing form just in the 7 minutes it takes them to be produced inside the sun and then reach us. By the way, this thing right here is a neutrino detector, because if you were thinking, you're like, wait, neutrinos just pass through matter. They're able to pass out of the sun like it's not even there. Photons, on the other hand, right, light takes 1 million years to get out of the incredibly dense, hostile environment of the sun. So these particles can just jump out of the sun, and scientists are able to detect them? How? The point is not very easily at all. So they build these unbelievably complex detectors. You can see this giant tank, all these sensing devices. They build them miles underground in abandoned mines. It's a huge procedure. They filled them with water, millions and millions of gallons of water. I mean, just the money they sink in these, like $100 million neutrino detectors, it's crazy. But that's the only way we can detect them. That's the only way we can know about the sun. And it's probably a good idea to know about the sun, considering it could just wipe us out, right? So how does nuclear fusion occur in the sun? Okay, really in summary here. The core's extreme temperature and density are just right for nuclear fusion of hydrogen to helium through the proton-proton chain. That was the fusion chain. Gravitational equilibrium acts as a thermostat. So the sun gets hotter or colder, it just regulates itself. Randomly bouncing photons carry energy through the radiation zone. The rising hot plasma brings that energy to the surface, and then that releases radiation to space, and we see that as the photosphere. And then we got models, vibrations, and neutrinos as our tools of studying the sun. Okay? So let's talk about the sun-Earth connection. I said the sun could wipe us out. It'd be unlikely, but entirely possible. There are a lot of things that do happen in terms of solar activity, okay? And then the variation of that solar activity of time, okay? So let's talk about this stuff. This stuff's cool, okay? Because the sun throws off huge plumes of hot plasma that are the size of planets, okay? And fly, well into Mercury's orbit. Mercury's not a great place to live, okay? There's sunspots, solar flares, solar prominences, and they're all related to one thing about the sun. It's got a magnetic field. Okay, so far, if you're keeping track, the Earth has a magnetic field. All the gas giants, especially Jupiter, have magnetic fields. Okay, the rest of the terrestrial planets don't. Magnetic fields are big deals for redirecting the solar wind. Okay, so turns out the sun has a huge magnetic field, but it's totally chaotic because the sun isn't stable like planets are, even Jupiter, right? You think, oh, Jupiter's got all big storms and everything, but it's fairly stable. It's fairly inert. The sun is not. All that energy production means this magnetic field is messy and complicated and constantly varying. Okay, so sunspots. Sunspots are spots on the surface of the sun. They appear dark. They're cooler than other parts of the sun, so they're 4,000 Kelvin instead of 6,000. All right, and essentially they're regions with a strong magnetic field. They're like magnetic field lines. All right, how do we know that? Well, there's something called the Zeeman effect. We can measure magnetic fields based on how they behave with certain atoms and the behavior of those atoms. They cause splitting lines in the atom. It's also related to something called not related, but it's similar to something called the 21 centimeter line. So when you hear me talk about that later in the semester, maybe make the connection. All right. So the idea essentially is that these charged particles spiral around the magnetic field. So if there's a spot where the magnetic field is really strong, then the charged particles are essentially going to take these helical paths and get sort of trapped there. Okay, that slows down their convection, which means that the regions with the strong magnetic field where all the matter is kind of trapped and swirling around means it can't naturally, heat up and rise and sink when it cools. And so they end up being kind of these like out of the way spots. They're spots where there's less convection, thus they're cooler. Okay? So, yeah. And by the way, they always form a loop. So from one sunspot to another, you can always follow the magnetic field by observing that Zeeman effect and making measurements of the atoms in the atmosphere there, the sun's atmosphere. Okay? All right, so magnetic activity also causes solar flares. So far we've talked about sunspots, which are dark spots that are on the surface. But what happens is that field line, that magnetic field that kind of goes up and makes a connection, well, gas can follow it. All right, and as gas follows it, sometimes it breaks apart, it gets highly energized. All right, and those send out bursts of X-rays and charged electrons, as well as charged protons. Okay, and they will fly out in space. They're high speed, high energy, and it's a good thing they get diverted from our atmosphere because over time they would degrade our atmosphere and the Earth wouldn't be livable. All right, it's not like they kill you right away, but they gradually cause molecules to break apart because they have enough energy to do that. Then there's also something called coronal mass ejections. These are like supercharged solar flares. They send bursts of energetic charged particles out through the solar system. So there, when a huge amount of matter gets pushed off, I mean, talking like millions of kilograms just getting ejected from the sun at high speed. It's like the sun just sort of spat out a bunch of matter. Okay, so those charged particles that are streaming away from the sun all the time, just because just steady solar wind, bursts from solar flares, even solar prominences. Here's the idea: they get redirected from our protective magnetic field. Okay, but when you have particularly strong aurora borealis, that might be because the sun is particularly violent or has just released a particularly large solar prominence. Okay? Now, activity varies over time though, and we know when to expect the most sunspots, and more sunspots means more of everything else. It means more solar flares, more solar prominences. Okay? That's when the surface is just particularly bubbly. Okay? Lots going on. The magnetic field is just going wild. Well, it turns out that it has an 11-year cycle. Okay? And we see that. Look at this. This is on the vertical axis. This is a percentage of the sun's surface covered by sunspots, right? Which just tell you how much the magnetic field is causing, X-rays to be produced and everything. Okay, and look, it peaks, and then falls off in 11-year periods. Peaks, falls off, peaks, right? And it's not perfect, but the trend is there. But notice that all the peaks are the same. In fact, it almost seems like there's a trend on top of a trend. Like, look, the peaks are getting gradually taller, okay? And then the peaks get gradually shorter, right? With, some variation, okay? Oh, that's interesting. So there's definitely an 11-year cycle. The 11-year cycle, manifests itself as sunspots, not just overall the sun, but they start every time at the equator. So the sun almost gets completely uncovered. It actually just happened last year. The sun was almost completely unblemished, not a single sunspot on it. And now it's already about a year and a half into the 11-year cycle. And so about halfway through the cycle, we're going to go from having just very few sunspots to them gradually being more and more clustered around the equator, right? And then starting to really kind of show up in the hemispheres, and then they just get denser and denser. So this is like a survey of the sunspots, see? And they move around. So even within years, right? They kind of swell and move and swirl around, but in this interesting predictable way. Okay? All right, but then how I mentioned there's a pattern on top of a pattern. There's additional variance because sunspot data has been recorded since the mid-1600s, in fact, the early 1600s, pretty reliably. There's always been some astronomer recording it ever since telescopes were good enough to do it. And so we see, right, there was incredible activity back then, and then it fell off, and then went up, right, and then it's kind of like there's something else going on. Okay, is it a steady pattern? Not exactly, right, but there's clearly been periods, right, where the activity in the early turn of the century, early 20th century, the 1800s and 1900s, we had particularly low activity. All right. Okay. This is showing that swirling magnetic field. Okay. See magnetic field shown here in the pink lines. This is like if the sun there was like something else other than the sun, like Jupiter, right? Nice steady magnetic field. But in reality, the sun is swirling around, and so the magnetic field ends up looking like this, messy and complicated. Okay, so stretching and twisting the magnetic field lines near the sun's surface cause solar activity, and it follows an 11-year period. Okay? Okay, so how do we talk about the brightness of the sun? Well, there's something called stellar luminosity. All right? And we'll get to that, and we'll get to other things, including the color and how that relates to the temperature. But that's all as we relate the sun to other stars. And that'll be the next video. All right? So thank you so much for watching this one. I hope it's really been interesting and informative. And please stay tuned for the second video covering Chapter 8. Thank you for watching.